Hello, everyone. My name is Zhen. I'm a fourth-year Ph.D. candidate in University of Michigan, advised by Dr. Henry Liu. Today, I'm going to talk about the integrated traffic signal and vehicle trajectory control in a mixed traffic condition. I think most of you have heard of connected and automated vehicles. They can communicate with other systems by V2X technology, sense the environment, and perform specific driving tasks with automation. Here, I give you two examples of connected or automated vehicles in University of Michigan. The first one is an M-Bus, which is a connected vehicle. The second one is a Navia shuttle running in M-City, which is automated vehicles. The current existing solutions to highly CAV, say SAE level 3 or higher, require multiple expensive onboard sensors. So if we look at the automated vehicle of Google, you can see that it has a LiDAR, it has radar, cameras, all different kind of expensive onboard sensors. It also requires complicated trajectory planning and vehicle control algorithms, which bring a challenge in real-world implementation, especially in urban traffic. One way to address this problem is to have the smart infrastructure. So this table is provided by researchers in Europe. So they define the infrastructure level. With the lowest level, we have the conventional infrastructure. And when we improve the smart infrastructure level, we can have the map information support to CAV, we have the dynamic information, say the weather condition, or we may provide cooperative perception so the smart infrastructure can perceive the traffic situation and provide those perception to CAVs. And finally, we have the cooperative driving smart infrastructure, which can provide support to CAVs and manage all vehicles in a mixed traffic conditions. So the key research question is that whether we can improve the smart infrastructure level to have lower requirement for CAV level. That's the reason why I proposed this cooperative driving framework, which mainly includes the two parts, the CAV module and infrastructure module. So we consider a mixed traffic condition in which we have the connected and automated vehicles. So those vehicles can broadcast their basic safety message, and they can also be controlled by some specific algorithm. We also have connected vehicles which are driven by human beings, but they can also broadcast their information. And finally, we have the regular vehicles, which is driven by human beings. They do not have any connectivity or automation. So for the connected vehicles, we consider the cooperation between CAVs. So we consider, so when several CAVs are close to each other, they can formulate a peloton. The peloton may split. And also for the leading vehicle of the peloton, it need to plan its own trajectory for the, it need to plan the trajectory for the whole peloton, whether the peloton need to stop, speed up, cruise, or slow down. The main functionality of the smart infrastructure is a signal optimization, which optimizes the time of arrival for each CAV at the stop bar and will be sent as a guidance to each CAV. So let's go to the details of the CAV module. We define 5 CAV control state: free flow state, intelligent follow, optimized control, launch, and stop state. So in this figure, we have the blue vehicle and the red vehicle as CAVs, and the black vehicle here is a regular vehicle. So here is actually the intersection. Before these 3 CAV enter the communication range, they are under the free flow state. So after they enter the communication range, the leading vehicle of the peloton will switch to optimized control state, and the following vehicle will switch to intelligent follow state. The leading vehicle, the blue vehicle, need to decide whether this peloton need to accelerate, cruise, decelerate, or stop at this intersection. So at this scenario, since the traffic signal is red, all those 3 vehicles just stop at this intersection. And when the signal turns to green, these 3 CAVs will switch to launch state and pass this intersection. After they pass the intersection, they will switch back to free flow state. I define a CAV control state transition diagram. Due to a time limitation, I cannot go to the details of this transition diagram, but I want to mention that by using this diagram, we are able to capture the pelotoning behavior, say 2 peloton merge into 1 peloton, or a peloton break into 2 peloton. Next is the infrastructure module. The first functionality is a queuing prediction. Basically, all the vehicles are sorted based on the distance to the stop bar. For connected vehicle or connected and automated vehicles, we can use their basic safety message to get the distance to the stop bar. For regular vehicles, we use an entrance loop detector to estimate their distance to stop bar. After that, they are searched successively to determine whether a vehicle will stop. With queuing prediction, we are able to provide the green window information for a CAV to say whether it can pass this intersection. Another very important functionality of the smart infrastructure is the integrated optimization. The objective is to minimize the total delay of all vehicles. And the decision variables are the signal timing plan and also the time of arrival of each CAV. Notice that we do not optimize the detailed trajectory, CAV trajectory at the smart infrastructure. The detailed CAV trajectory is solved in the CAV module. In this way, we reduce the computational burden at the smart infrastructure. So here is the mixed integer linear programming we propose for the signal optimization. The objective is to minimize the total delay of all vehicles approaching this intersection. So the first constraint is how do we calculate such delay? And we also have a group of signal constraints which represent this ring barrier diagram. We have the time of arrival constraints in general, which determine whether a vehicle will stop or not. And also we have the CACC specific time of arrival constraints, which determine whether a platoon will split or not. Here is the simulation analysis. Let's first take a look at the right figure. So here is the simulation framework. The simulation is conducted in vSim, which has the signal controller to control the traffic signal. We have different kinds of CAV and connectee and CAV and RV. As I just mentioned, in the CAV module, we have the speed profile generation. In the infrastructure module, we have the queuing profile prediction and signal optimization. So after the signal optimization, the optimized signal timing plan will be sent to signal controller, and the arrival time will be sent to CAV module to plan its trajectory. After the simulation, we'll use the post-analysis module to get the fuel consumption and emission. So we use the intersection of Plymouth Road and Murphy Avenue in Ann Arbor, Michigan. The baseline we have is actuated signal control. And basically, we conducted two groups of experiments. With the first one is with CAV and CAV. The second one is with CAV and RV, and under different penetration rates. So here is the results of the first group, CAV and CAV. So we give you the performance of the mobility in terms of total vehicle delay and number of stops, and also give you the performance of the fuel consumption in terms of CO2 emission and energy consumption. So you can see that as we increase the penetration rate of CAV, we can have better and better performance in both mobility and fuel consumption. The second group is with CAV and RV. In general, the performance is still similar. When we have more penetration, we have more CAV, we can have better performance in terms of mobility and fuel consumption. There's just one thing for the number of stops. As you can see, if we increase the penetration rate, the performance goes worse a little bit and then goes better. The reason why we have such performance is that with regular vehicle, we cannot estimate the queue length very accurate. So that actually leads to a bad performance when we have more CAV. So in the conclusion, I proposed a cooperative driving framework in a mixed traffic condition of regular vehicles, connected vehicles, and connected automated vehicles. At the CAV module, we proposed a CAV control state transition diagram for different operating modes. At the infrastructure module, we optimized the traffic signal and also the CAV time of arrival with a mixed integer linear programming problem. The simulation results of a signalized intersection shows the benefit of mobility and fuel consumption, and the delay reduction can be as high as 18.7% on the high penetration rate of CAVs. Notice that we also extend this work to a traffic corridor in which we consider the coordination between different intersections. Due to time limit, I cannot present that work here. And that's all I have. Thank you.
Maybe I'll ask you about the definition of connected vehicles as opposed to connected and automated.
Yeah, so for the connected vehicles, they are driven by human beings, but they can provide basic safety message through the onboard unit. For connected and automated vehicles, they are not only provide such information through connectivity, but they are also controlled by some specific autonomous driving trajectory planning algorithm.
Thank you.
Yeah, thank you.
Yes, I have a question. You said you tested this on some fuel economy and mobility. Can you kind of not the fuel side, but the mobility side. Can you show what kind of benefit you saw from the mobility aspect? What is it?
Yeah, so for the mobility side, you can see that as we, so these two figures shows the total vehicle delay and number of stops when we have different penetration rate of CAVs. So as we increase the penetration rate of CAVs, the total vehicle delay and number of stops decrease. So that's the mobility performance.
I see. So that when you said the total vehicle delay, the total vehicle delay in driving time?
Oh, yes, exactly.
Yeah, okay.
Yeah.
Driving time and other stuff. And did you look into any kind of safety aspect? So while you're optimizing these other things, is there anything on the safety side that's getting disadvantaged, or that safety is always maintained while you're doing these things?
Yeah, that's a very good point. So actually, due to time limitation, I'm not able to mention that, but we do, when we design the CAV trajectory planning algorithm, we do consider that they have the collision avoidance, to avoid collision with other CAV. Yes, yeah, thank you for your question. That's a good question.
Thank you.
Thank you.